Hi, this is Professor B.K. Navle from Bhimrao Sawant College of Engineering and Research, Nare, Pune. And today we will see one assignment from VLSI Design and Technology. The assignment is to implement CMOS inverter, NAND, NOR and half adder in microWIN. Part B. In Part A, we have seen how to implement CMOS inverter in microWIN. Now, in this part, we will see how to implement NAND and NOR in microWIN. The NAND is nothing but AND with NOT gate, and the output of two input NAND gate is low when both the input is high. Otherwise, the output is high. The CMOS NAND gate is the combination of two P MOSFET and two N MOSFET. Here VA and VP are high, then P MOSFET will be open circuited and N MOSFET will be short circuited. That's why Vout is grounded through N MOSFETs and which produces 0 at the output. If any input is low, corresponding P MOSFET is shorted and N MOSFET will be in open state. So Vout is shorted to VDD through particular P MOSFET and which produces high at the output. As we require 2 P MOSFET and 2 N MOSFET, just go to palette, click on MOS generator. The layout generator window will pop up. Okay, now change unit to the lambda and we will take minimum width for N MOSFET, that is 4. The minimum length for N MOSFET is 2. Okay, now we require 2 N MOSFET, that's why we will change number of fingers to 2. That will gives you 2 back-to-back N MOSFET. Now click on generate device and click in the grid area to produce the 2 MOSFET back-to-back. Okay, so you have 2 N MOSFETs in which this may be acts as a source of first N MOSFET and this will act as a gate for the N MOSFET. This may act as a drain for the MOSFET 1, N MOSFET 1, and same pin can be act as a drain or source for MOSFET 2. This will act as a gate for N MOSFET 2 and this will act as a either drain or source for N MOSFET 2. Okay, similarly we will generate P MOSFET. Again click on MOS generator, then change this width of the P MOSFET to near about 2 to 3 times of N MOSFET. Now we will make it 9. Okay, then number of fingers will be 2 and change type of device to P MOSFET and click on generate device and to paste the P MOSFET click in grid area. Okay, now arrange the N MOSFET and P MOSFET if required. Now click on zoom on so that you will have a good view of all the components that we have on the screen. Okay, now we have to connect a source of both P MOSFET to the VDD. So we can consider this as a source of P MOSFET 1 and this will be act as a drain of P MOSFET 1. Okay, again this pin will act as a drain of P MOSFET 2. This will act as a gate of P MOSFET 2 and this will act as a source of P MOSFET 2. So we have to connect source of P MOSFET 2 and source of P MOSFET 1 to VDD. So we will extend source of P MOSFET 1, okay, and source of P MOSFET 2, and we will connect both sources through metal 1. And we will provide common VDD for both sources. Again, we have to provide VDD to N well of P MOSFET. Just go to palette, click on VDD and place it in N well of P MOSFET. Now we have to connect drain of the both P MOSFET to the source of N MOSFET 1. So we will extend the source of N MOSFET 1 by using stretch move tool. Okay, click on the edge of the source of the N MOSFET 1. Now similarly stretch the drain of the P MOSFET. Okay, again to connect both I will going to use metal 1. Okay, just place a rectangle box and you have the connection between drain of P MOSFET and source of N MOSFET 1. Okay, now this will act as a drain of the N MOSFET 1. Same pin will act as a drain for N MOSFET 2, and this will be the source of N MOSFET 2. Okay, so we have to connect this source pin to the ground. So go to palette, click on ground and place it in source area of MOSFET 2. Now we have to provide supply VA for 1 P MOSFET and N MOSFET 1. So we will connect gate of the P MOSFET 1 to the gate of the N MOSFET 1. Though there is a crossing between polysilicon layer and metal 1 layer, as they are of different type, there is no direct contact unless and until we provide metal to poly contact. So they are not shorted to each other, though there is a crossing of metal 1 and polysilicon layer. We have to connect gate of P MOSFET 2 to the gate of N MOSFET 2. Okay, go to stretch, click on the edge of the gate of P MOSFET 2 and stretch it to the gate of the N MOSFET 2. Now go to palette, click on add clock and place it on gate of P MOSFET 1 and N MOSFET 1. Okay, give the name for the input, let's say A, which will be the input 1. Okay, and you can see the load time is 0.225, rise time is 0.025, high time is 0.225 and fall time is 0.025 nanosecond. So assign this clock as a input 1. Okay, click on assign. Similarly, we have to apply second input to the gate of P MOSFET 2 and N MOSFET 2. So go to palette, click on add clock, place that clock on the gate of P MOSFET 2 and N MOSFET 2. We will be giving name B, that means input 2, and the load time is 0.475 and high time is 0.475, which is the double as that of input 1. We have to do the changes if that is not so. Okay, then click on assign. Okay, now we have to see the output. Okay, I will little bit extend this common point by using metal 1. Okay, then I will assign output node, that is visible node, to the drain of P MOSFET and source of N MOSFET 1. We will be give name for output node as a Y and then click on assign. Now go to DRC, check whether we have some error in our design, and if we don't have any error, right now we don't have any error, no design error, so click on simulate design or run simulation. Okay, now you can see when both the input are high, the output of NAND gate is low, otherwise the output of NAND gate is high. And you can also note what is the power dissipation is 1.696 microwatt. Okay, now we will see what is the effect of adding the capacitive load in same NAND circuit. So just go to design, go to palette, click on add virtual capacitance and place that capacitor at output part, that is near to output node. Okay, the value is 0.01 picofarad. Click on OK. Go to DRC and check if we have any error in design. Then click on run simulation to simulate the design. And now you can see the rise time is 20 picosecond and fall time is 30 picosecond. So both rise and fall time are increased due to capacitive load. You can also see that the power dissipation also increased due to adding a load capacitance. So this is for NAND gate. Now we will see working of NOR gate, how to implement NOR gate in microwind. The NOR gate is nothing but OR gate with NOT gate, and the output of NOR gate is high when all the inputs are low, otherwise the output is low. As shown in figure, CMOS NOR gate consists of 2 series P MOSFET and 2 parallel N MOSFET. Input 1 is applied to P MOSFET 1 and N MOSFET 1, and input 2, that is B, is applied to P MOSFET 1 and P MOSFET 2 and N MOSFET 2. The source of P MOSFET 1 is connected to VDD. The drain of P MOSFET 1 is connected to source of P MOSFET 2, and the drain of P MOSFET 2 is connected to drain of N MOSFET 1 and N MOSFET 2, and the sources of N MOSFET 1 and N MOSFET 2 is connected to ground. So we have to make such connection in microwind also. Okay, this is the layout for CMOS NOR gate. The source of P MOSFET 1 is connected to VDD. The drain of P MOSFET 1 is common with source of P MOSFET 2. This will act as a gate for P MOSFET 2. This is the drain of P MOSFET 2, which is connected to the common terminal for N MOSFET 1 and N MOSFET 2, which will act as a drain for N MOSFET 1 and 2. The source of N MOSFET 1 and source of N MOSFET 2 is connected to ground. Also, input 1 is applied to P MOSFET 1 and gate of N MOSFET 1, and input 2 is applied to gate of P MOSFET 2 and gate of N MOSFET 2. Now we can observe the output at drain of P MOSFET 2 and drain of N MOSFET 1 and 2. So let us check DRC. As we don't have any error, click on run simulation to simulate the design, and you can see that when both the input are 0, the output is 1, else output is 0. Okay. Also note down the rise and fall time. Rise time is 7 picosecond and fall time is 5 picosecond. Also note power dissipation, that is P is equal to 1.61 microwatt. Now we will add capacitive load and see what are the changes we will see in rise and fall time. So go to palette, click on add virtual capacitance and add it to output terminal. The value of capacitance is 0.01 picofarad. Click on OK. So simulate the design once again, and you can see the rise time increases to 36 picosecond and fall time also increases to 32 picosecond. Okay. Also you can see what is the power dissipation, 14.25 microwatt. So from this we can conclude that by adding the capacitive load, the rise and fall time as well as power dissipation increases in CMOS NOR gate.